Hey Year 12. So I'm going to make some videos for you guys on chapter 23, which is, I've put it in your OneNote here. It's under just tab number 21, discrete random variables. And it goes A, B, C, D, but D is 1.1, 0.2, and 0.3. Okay. So this actually ties in really nicely with our binomial theorem topic, which we just finished, but it will come towards the end of this chapter, and it'll actually be, I think, really satisfying. You'll see that it just makes sense, and it's like a nice shortcut into how to find probability of certain events, and it ties it all in together really well. So 23A is about discrete random variables. So let's just go through really quickly the definition. This is actually stuff you've all seen before, but the notation is just different. So I'll try to highlight as I go along so you can see where I'm pointing to on the screen and read along. So we've got random variable, right, represents like all your possible outcomes in any sort of random experiment, but it is in number form. Okay, so it makes it sort of easier to calculate or to use in different situations. So a discrete random variable, and we're going to call it capital X. Okay, if you remember back in like say year 9 or 10 probability, you looked at these two words. You looked at the word, let me highlight in blue for you, discrete. And you also looked at the word continuous when you learned about different types of data, like qualitative, quantitative, continuous. You might have used the word discrete, but you've actually come across the idea. So it's when you have distinct possible values. So like whole numbers, basically, like integers, okay? So it could be, for example here, like, let's just say the number of houses in your suburb which have a power safety switch, number of new bicycles sold each year in a bicycle store, number of defective light bulbs, etc. You can see they're all integers, right? So that's what discrete means, distinct possible values that are whole numbers. And so we label them as, x1, x2, x3, etc., xn. Now, when it's continuous, okay, so you looked at continuous data back in year 9 and 10. So this is like a number where it's not integers. So it's usually like on a continuum, or you could say that it's on an interval, like on a number line. So it's something that you have to measure. So that's kind of a nice way of putting it. Discrete is you need to count it, and then continuous is you need to measure it. So it could be something like the heights of a bunch of people, and the height could be anything between 50 say to 250 centimeters, right? So you can get like 241.2, etc. Okay, so it's not like complete integer numbers. Okay, so now with your random variables, let's move down, sorry if I'm flicking a bit too fast. You've got a corresponding probability distribution. Okay, and that describes the probability that the variable will take any particular value. So this is the notation here. So if we're talking about a variable x, okay, the probability that that is going to happen for this particular value, little x, we call it this. You write capital P bracket capital X equals little x bracket. Okay, this will make more sense if we actually go through an example. So if you have a look here, let's say I'm tossing 2 coins. Okay, the random variable x could be, let's say we're looking at just heads. Okay, so we're looking at, we've got, you could get 0 heads, 1 head, or 2 heads. So like that's your whole sample space. That's all the results that you can get. Does that make sense? So x, capital X could be, I'll highlight in blue here, x could be 0, 1, or 2. So the event is heads, but remember we now express it in number form. So the possible outcomes are 0, 1, and 2. Okay, it represents heads, but we do it with just numerical now. Okay, so 0, 1, and 2. So we will write it like this. Capital P, bracket, capital X equals, or the random variable x, to be 0, which means to give 0 heads, is 1/4. The probability of getting 1 head is half. And the probability of getting 2 heads is 1/4. Does that make sense? But instead of writing like, we used to write P bracket like say 2 heads or something like that, okay? Instead of writing all this mess every time, okay, we're just saying like an X is just this general notation for the event, okay, that we want, and then the number that actually represents, how many of those, does that make sense? 2 other ways of expressing the range of your probabilities or the probability distribution is through these types of graphs. So there's a spike graph and a probability column graph. So spike graph just looks like this. So you can see for 0 heads, you have a 1/4 chance. Getting 1 head has a half chance, or probability, sorry, same thing. And 2 heads is 1/4. Okay, so you can kind of just see the spread. Column graph, same thing, right? It's just that it's columns. So let's have a look at one example. Let's do one. So if you have, say, a supermarket has 3 checkout points, A, B, and C. A government inspector checks the weighing scales for accuracy at each checkout. If a weighing scale is accurate, then Y is recorded. Maybe think of Y as yes, okay? So yes, it's accurate, it's recorded. And if not, N is recorded, okay? N for no. Suppose the random variable X is the number of accurate weighing scales at the supermarket. Question A, list the possible outcomes. Okay, so we have to sort of write this out a little bit. It might be easy if we do it in a table. Now let's actually go back and highlight some information. So if the scale is accurate, Y is recorded. If it's not, N is recorded. Now your variable X, random variable X, is the number of accurate weighing scales. Okay. Now the thing is that we've got scales at A, B, and C. Okay, 3 different checkouts. Let's have a look. And the random variable X is the number of accurate weighing scales you could have. Okay, because you could have, so for example, I'm going to rule this off. It'll be easy to see. So let's say, it's not accurate at A, not at B, and not at C. So the X, the number of accurate weighing scales, is 0. Yeah, at this supermarket. Does that make sense? So let's say A has one that is accurate and the rest no. So I'm just kind of just doing this systematically so I get everything. So X, there happens to be 1. Does that make sense? Just like how earlier we said, getting 1 head, yeah, is capital X equals 1. Random variable X is 1. So let's just go through and do all of these ones. So let's say this time that's no, and then yes, no. So that's 1. And let's say this time it's no, no, yes, which is still 1. Okay, now that's all the combinations I could do for 1 accurate scale. Now I've got to do 2. So maybe yes, yes, no. So that will be 2. And let's say we go yes, yes, no, yes, which is 2. And then you could have no, yes, yes, 2. And then that's it, isn't it? Okay. Because no other places to put it to make it different to these 3. Okay, and then these ones are kind of together. Okay, and then we could also have yes, 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 right? All 3 accurate. And so then we've got 3. Okay, so that's like part A, just listing out all the possible outcomes. Now part B, okay, describe using random variable X the events of there being 1 accurate scale. So this is actually just getting you, it sounds really silly, but it's just getting you used to the notation. So if you're saying there's only 1 accurate scale, you're saying capital X equals 1. Does that make sense? So it's like this one, or this one, but it's just asking you to write the notation. So and then part 2, this is where the language is important. It says at least one accurate scale. So if I want at least one, that means I have to have 1, 2, or 3, right? But just not 0, not just none. So all you've got to do is x has to equal to 1, 2, or 3. That's it. Okay, so what you guys need to do for this one is the homework is exercise 23A, and it's on page 609. Okay, let me know if you have any problems. You can always send me a Schoology message or an email, or put it in the OneNote and ask other people to collaborate and help and work together as well.